I realized rather late that in spite having designed the assembler engine and even prepped all of the stuff I needed to produce a video about it, I never did it. This was the first engine I designed with a 1:5 factor split after I had found it on the Satisfactory calculator website. The version on the Satisfactory calculator website is the 2 to 2 mix, where you take two splitters taking in two different items, you split them both into two mergers, so each item is divided into half, and you have even mixes of both items. But this I designed for just one item. It takes the item in at whatever part per minute it is, and then it divides it into the two mergers. They each go to the last two splitters, and 1/6 gets merged back in, half and half, back into the mergers. Mergers. And in that way, you are actually able to immediately take what would normally be split into 1/6 into 1/5, because 1/6 of it is immediately recycled back into the system, which is a little confusing math-wise, but the feedback increases the rate per minute that these mergers are collecting items. And this is the first engine I designed specifically for 20 machines because that seemed like a convenient number to work with. 4 sets of 5. It also makes it much easier to come up with a whole part number to split 4 ways before it goes into the factor splits. And you can work with as large a number as possible. And it's a lot easier to create that specific number you need with belt math. Instead of having to math out the number of parts per minute for every factor split or for every machine, you have in total one large number of items that gets split multiple times into smaller increments and often decimal increments of parts per minute. The original design I made let's just say the concept is a little incomplete. I'd originally decided to take one full belt of the copper that I need for the fused quick wire at 780 parts per minute, even though I only need 750, and I would overflow the last 30 out. It didn't occur to me that I could simply just take the 30 off beforehand and then split everything evenly. It did occur to me to do that with the Caterium, which I only need 150 of. But apparently not the copper the first time I designed this. So the belt math does get done for every 4 machines for the copper ingots, and I found that was inefficient space-wise. It can be done, but it's awkward, and you have to come up with a different solution for every part count. Instead, well, this is just the other fused wire recipe at 480 copper and 120 Caterium, and I made it twice as tall because that amount of copper and Caterium feeds 40 machines, not 20 machines. Of course, that's a bit ridiculously tall. Next time I build this for a project, I would definitely build them side by side instead. But for any number of other recipes, like this is stitched iron plates. This belt math thing, this little bit of belt math is creating 375 parts per minute. So how it works is I start with a Mark IV line at 480 parts per minute. A smart splitter force feeds a Mark III line at 270 parts per minute, and the remainder flows into the next splitter. The remainder is 210 parts per minute. That gets split in half, so 105 parts per minute gets added to the 270 to create 375 parts per minute. That gets divided 4 ways, and then 5 after that into 4 machines to create an item count of 18.7 parts per minute per machine. And the wire is 37.5, which is the same as the copper in the fused quick wire recipe. So that's kind of the same math that I chose to do with the copper over there the next time I built that machine. I start with a Mark V belt. I take off 60 with a Mark I belt. 30 goes back onto the line. So it's 750 parts per minute going to the machine. That gets divided 4 ways, then 5 ways into 37.5. Now there's any number of ways to actually divide and load machines. So 150 parts per minute with 450 parts per minute for rubber and iron plate makes adhered plate 150 parts per minute. That feeds 40 machines. 150, there's 2 ways to do 150 parts per minute. You start with a Mark III belt, you take off 120 with a Mark II belt, you're left with 150 parts per minute. The other way is you take 120 parts per minute, add half of a Mark I belt, that also makes 150 parts per minute. 450 parts per minute is just like the Mark V line math. You take off 60, add back 30, 450 parts. Just starting with a Mark IV line instead of a Mark V. The conversion cube, that's literally 1 to 2 parts. So, and it only consumes 1 set of those every minute. So that's literally 1 part and 2 parts for the fused modular frame and the radio control units at literally 60 machines. That's to create 60 pressure conversion cubes. And I think that's the only recipe, so it's a very energy intensive recipe. Coated plates, 100 parts per minute you can make easy. These are both Mark I lifters. And I'm dividing into a Mark I belt into 3, so that's 40 is getting added to a Mark II belt. So 40 plus, is that a Mark II belt? No, it's a Mark I belt. 40 is getting added to 60 parts per minute to make 100 parts per minute. 500 parts per minute, it's Mark IV belts plus 20 parts per minute, 500 parts per minute. 300 parts per minute is, yes, these are removing 300 parts per minute. You remove 60 and 120 parts respectively, so that's 180 parts off of 480. That creates 300. The same trick can be applied to a Mark V belt to create 600. 180 off of a Mark V belt is 600. That's also a nice number to work with in some recipes. 450, we already know that. This right here is the revealed framework. Every single factor split has to be offset so that it lines up with each input. There's likely a way to fit in a 2 mix to 5 split, so you can have both items onto one factor split tree, but I really don't feel like redesigning this thing, and that would be pretty tight down there. Trying to fit both split trees in the same area instead of the first split tree on the first 2 layers and the second split tree on the second 2 layers is a little a little much. Of course, you can also work around with the design if you have different parts per minute needs. For example, I showed this whole production line in the 240 stators per minute video. Nobody really watched it, but this is where I had originally introduced the assembler engine, because I just went ahead and did this before I was ready to actually reveal my idea. Because I wanted to see how many stators I could make out of 720 solid steel per minute. So starts with 480 iron ore into iron ingots. That gets added to 480 coal into 12 machines. That becomes 720 steel. That 720 steel gets turned into steel pipe, and that's 480 steel pipe. The quickwire engine, the fused quickwire engine, was the recipe that just really nicely lined up with the parts per minute needed. So this produces 1,800 fused quickwire per minute, and that's exactly what I needed to make fused, to consume all the 480 steel pipe per minute to create quickwire stators. I had originally thought I'd used control flow, like Mark 1 lifter that would always be full because there's always parts flowing through the belts. Not quite true, because every single one of these belts coming out of every 5 machines is 450 parts per minute. So there's a few seconds gap between each shunt of parts, and that can create gaps if I try to force load a Mark 1 lifter just from a splitter. So I eventually found another solution where I would take every 2 lines of 450 parts per minute, split both lines 3 ways, and combine it into 3 mergers. 2 belts of 150 quickwire per minute into 3 belts of 300 quickwire per minute. Every 300 gets moved into a 1-to-5 factor split. That's the 60 parts per minute needed for the recipe. And the third belt goes through the center, gets collected with the second layers, gets up to the third layer, gets split 2 ways, so there's 300 going each way, and that's how everything was much more efficient. There's still a stutter, but it was much more predictable. It did actually get up to 100% efficiency much more quickly. As for the one line of 480 parts per minute for the steel pipe, that I took and split 6 ways instead of 4. And that made things really tight to work with, unfortunately. So even though I wanted to design my solution for splitting up the 450 part belts a little differently, a little further in, it was just too tight, so I had to settle for a little jury rig. I know this has been a bit long-winded, but this was the first engine I designed completely myself, instead of just adjusting Kibit's engine design. And that became the basis for the manufacturer engine, the mixer engine, the refinery engine. Honestly, the only other thing that I have not designed for proliferously is the constructors, and those are largely just controlled flow. Like, you fill up a Mark 1 belt or a Mark 2 belt and you split it 2 or 3 ways to achieve 30, 40, 20 parts per minute, what have you. There may be some instances where a factor split would be more useful for like a 1 to 5 would create 12 parts per minute quite easily from a Mark 1 belt, or 24 parts per minute from a Mark 2 belt. Yeah. I just felt I finally need to get this video out and properly enunciated. Apologies for not keeping it quite succinct. Yeah. That is the rough design of the assembler engine. As long as you can produce a large number that you can divide evenly and then split 5 ways with a factor split, then you can easily load an assembler engine comparatively to other methods. At the very least, it's quite repeatable. And when you do know how each of the elements works, you can readjust your needs to the recipe, like I did with the stator engine. Whoa. Hi there, buddy. There's plenty of things that I actually have not mathed out the recipe for. I just came up with this way to actually figure out how many parts I need. You start with the item of parts per minute that you're consuming, the first 5 set of machines, which is in one array of 5, the 5-factor split, and then 4 sets, and that equals 1 engine. And that's how many parts you need to load. You can adjust how many engines you can load or need to load as you can see what limits or difficulties you'll have coming up with a whole number to put through one belt. There are definitely opportunities to do multiple engines with fewer belts than you might expect. Like the 375 parts per minute for the iron plate. Right now, there's 100, the way the math works, there's 105 parts being sorted back into the system, or at least once this thing clears out, once I connect it up. You can instead use that 105 parts, add it to another Mark III belt, and just have another 375 parts to load another stitched plate engine. You can literally carry all the plates you need with one Mark IV belt and one Mark III belt. I actually should probably show off one of these things. Just let it go. Now, because there's no mixing, these things load very fast. They'll almost all turn on at the exact same time. Except apart from like belt lag. It's not quite as fast as the smelters, unfortunately, depending on the recipe. It does take roughly a minute. There we go. They're all on. And in about a minute, or no, in about half a minute, there'll be 112.5 steel plate, well, reinforced plate per minute coming out of the engine. Of course, because of how the belt math works, there is some excess still in the system. Nope, it's all cleared up. That's got its gaps every now and again. And this definitely has its gaps. And there we go. That didn't take long. There is one thing I notice about, like, lining up engine after engine to have specific parts going from one engine to the next. While startup is quick, going from one engine to the next, because it's not all immediate, you can have some time delay between each engine successfully coming fully online, because not all the parts are being produced immediately, because the belt's not from the previous engine is not being filled immediately. So while it is extremely part efficient, it won't carry over every advantage of immediate startup. It'll definitely be more advantageous than any form of overflow manifold, but it won't be instantaneous as if you're just working with one engine. If you work with multiple engines, one after the other, there will be some exponential time delay. Yeah, that's a lot of my thoughts on engines. They're not all controlled flow, they're not all perfect split, but combining the two, you can definitely utilize the benefits of both. Anyways, thanks for joining me, and I'll see you when I see you. Bye.